Expectation gets used a lot to talk about a final general property of random variables and their mass functions. So the final idea here is that we are going to worry about the spread of a random variable. So what I mean by that is, in these two pictures that I've drawn, these just represent some mass function of a random variable x. And it turns out that they both have the same value of mu. But just because they have the same expected outcome doesn't mean that these mass functions are the same at all. And when you look at their bar charts, you can tell very much that they're different. There isn't a lot of what we call spread here. Everything in this first example seems to be bunched up quite closely to the mean, whereas in this second example, things have a lot more variety. They are quite spread relative to the mean. So we use this word spread very loosely. What we would like is a way to measure spread. Now there's something very simple called the range, and the range is where you would take the max value of x and then subtract it from the minimum value of x. And in some way, that's what our eyes see when we take a look here. So this would be the range in the first case, whereas in the second case, it would have a much larger range. Now, the range is a nice simple value, but you can't do much with it. And it's going to turn out that for the theory of probability, the range isn't very useful. So it's what we'll say is it's not robust enough for probability theory. And as we go in this first part of the course, we will talk a lot more about what that means. Okay. So another idea is the following. We're going to, we're going to try and measure how far each outcome xi is from this expectation, or from the mean, or from this value of mu. And so we will say that a deviation of xi, the word deviation is root word is deviate. It means to go away from something. And so xi minus mu is the deviation from the mean. So that just tells you how far away that value is from the mean. And if you look at these pictures above, this value of xi right here has quite a large deviation from the mean, whereas this value of xi has a small deviation from the mean. It's closer. So the plan is we're going to measure each deviation of the mean. Oops, sorry about that. And then average all of the deviations. And averaging the deviations is kind of like talking about expectation, because an expectation is the most likely, or what we call the average outcome. But there's a little bit of an issue. If we try to take the expected or average value of all of the deviations, we end up getting 0, always, for any random variable. And we proved this earlier with the expectation properties. So that's too bad, because I think a good way of measuring spread is to see how far each outcome is from the mean. But mathematically, every probability mass function behaves in this way, that it will give you an average deviation of 0. So that's kind of unfortunate. But math people said, well, let's go to the next best thing. And maybe best is a bit too vague, or easiest idea is that we are going to take the square of the deviations. It's the next level up in terms of complication for a mathematical idea, but it's not too difficult. And so what ends up happening is we take the square, the expectation of the square deviations. So we will go this thing squared, and in terms of the definition, we'll be taking xi minus mu and squaring it and then weighting it. So this is what we are going to define as the variance of this random variable. And so the notation will be variance of x. Sometimes we'll write it with the Greek letter sigma, lowercase sigma squared, and it will be this summation. And the variance measures the average of all the square deviations from the mean. So it's the average value of all the squared deviations from the mean. And again, its job is to measure spread in some way. Now, note that the variance is always a positive number. And that's kind of why they call it a sigma squared. Because by definition, if you take a look at how this formula is constructed, all probability values are always greater than 0. Squaring something is always greater than 0. So the variance will always be a positive number. The variance will only ever equal 0 if and only if all of the observations are equal to mu. And that means there is no spread. So when all of the outcomes of this random variable are the same, then you'll get a 0 variance. There's no spread. You'll essentially just have a bar chart with one large value. Now, this definition above is what I'm going to call the conceptual definition of variance, because this is the idea, the concept that you use to construct it. But it's really inconvenient if we need to calculate variance. And that's what our ultimate goal is. We're going to want some number that tells us about the spread of a random variable and its mass function. So instead, we have an alternate formula. So if we take the definition of variance and we take a look at its summation formula, we can just apply basic algebra and simplify the way it looks. Now remember, the mu is a constant here. This is the average or the expected value of our random variable, but we are now interested in calculating a different thing, this spread. And when we do so, we can separate things out and use summation properties to simplify how this stuff is going to look. And so just by using basic algebra and basic summation properties, we end up with something that on the surface looks a lot worse. We've taken that expression out and we've foiled it, we've expanded it to get to some mess that looks like this. But in fact, this is going to be a lot nicer. We know from the definition of a mass function that has to be a 1. And we know by definition this is the expected value. So what this allows us to do is come up with another way of writing variance. We'll get minus 2 mu squared plus another mu squared. And so what we'll end up with is that the variance here is xi to n xi squared with a pi minus a mu squared. And another way of putting this is that this would be the expectation of the variable squared on the inside minus the square of the expectation on the outside. And so this ends up being a handy little formula. This is what I'm going to call the computational version of variance. And when it comes time to getting a number, this is the version that we're going to use. Now, there's one final idea that we get before we can jump into a calculation. And the idea here is that the units of variance don't match the units of the random variable. So if your random variable has units of kilograms, because you are squaring the deviation, the units of variance would be kilograms squared in some way. So math people have said, you know what, in order to balance units, so to have some sort of spread measure with the same units, we define the following. We define something called standard deviation. So the standard deviation is just essentially the square root of the variance of x. So whatever number you find for the variance, you take its square root. And so it ends up being pretty easy to calculate. There's a lot of discussion that goes on to get to the concept of variance. But once you get the concept of variance, it's not so difficult to use at all. So on the PDF that's attached here that has the definitions, it also has a first example, the example with the public speaker. If we are interested in the expected value, we can sit there and calculate it directly. We would take all of the outcomes and then weight them by the probabilities. So her estimate of 0 speeches a week would have a probability of 0.06. 1 speech a week would be 0.42. And then we would take this all the way down, 5 speeches at a probability of 0.03. And if we go ahead and we calculate this, mu will be 1.97. Okay? Which means, on average, this speaker expects that if she kept doing a week at a time of speeches, week at a time, and averaging them all, on average, she expects about 1.97 speeches per week. So that helps give an estimate of what will happen. Now, the variance can be calculated with the computational formula. E of x squared minus the expectation all squared. And we like using this version because it's pretty straightforward once you've calculated the expectation. Then the only thing that's left to do is to take the values directly and calculate this first term. And this first term is just as easy as one extra step. It works with the values directly. So for example, this would be 0 squared times 0.03, outcome 1 squared times 0.42, outcome 2 squared times 0.22, all the way down the list, 5 squared times 0.03. Once you calculate this number and you plug it all in, sorry about that, you end up getting that the variance of x, once you put it all together, is 1.6491 speeches squared, whereas then the standard deviation, sigma, would just be the square root of this value, would end up being about 1.2847 speeches per week. And that's why we like standard deviation, because it has the same units as the data. Okay? In the next video, I'm going to talk a little bit about an important property of variance and why we might want to use standard deviation.